Hello again, this is Mr. P, and we are going to look at some more properties of waves. Okay, so this would be the your e-learning lesson for Wednesday, April 8th. Okay, so far we've looked at different types of waves, right? Transverse, longitudinal. We've looked at some properties of waves like speed, amplitude, frequency, period, and how all those relate. In this section, we're going to look at some different phenomena of waves that occur when waves interact with other waves, other surfaces. So reflection, refraction, diffraction. We're going to get a better understanding of what all those mean in terms of waves, and see different examples, some illustrations, some demonstrations, and let's go ahead and let's look at the first term here, which is reflection. So you may have heard this term before. So this is when an object or wave hits a surface through which it cannot pass. Okay, and it bounces back. All right, so just think of paper ball hitting a chalkboard, can't go through it. It bounces back, it reflects off of the board. Same thing happens with waves, like sound waves and light waves. Let's just talk about it first in terms of light waves. Let's say we're looking in the mirror. Okay, light strikes our eye and is reflected into the mirror. Then the light reflects off of the mirror back into our eye. Okay, and we're able to see our image in the mirror. That's what allows us to see ourselves in the mirror. Sound, okay, reflection of sound we can talk about in terms of what we call an echo. Okay, and I'm sure we've heard that term before, an echo. So that occurs when sound reflects or reflects off or bounces off, okay, another surface. So right now, the room is empty, and my voice is reflecting, okay, or echoing off of all the surfaces. Let's, for example, the walls. So I'm able to hear myself, my voice, after I speak. I'm able to hear that sound come back to my ears in the form of an echo. It reflects back off of all the surfaces in the room. Or I whistle, and I can hear that sound reflecting back after I whistle in the form of an echo. It's reflecting off of all the hard surfaces in the room back to my ears in the form of sound waves. All right, so with reflection, okay, what this said, the law of reflection says that the angle of incidence is equal to the angle of reflection. So the angle of incidence, that's the angle that a wave initially strikes a surface. The angle of reflection, that's the angle at which it is reflected or bounces off, and those two angles are the same. So let's say this light hits the surface, maybe the mirror, at 45 degrees. It's going to reflect at 45 degrees. Okay, and we can see here a diagram of reflection, right? The original wave, the blue wave, is traveling to the right. When it bounces off this surface, maybe a wall, then the reflected wave travels to the left, and we'll see later something occurs called interference, where the two waves combine with each other. But for right now, just remember that the wave traveling to the right bounces off, and the reflected wave travels in the opposite direction to the left. So let me show you a demonstration. Okay, so again, the point down, the object down here represents a surface that the wave is going to bounce off of. So if I send a wave to the right, notice that it's reflected back to the left. So notice once again, original wave travels to the right, boom, reflects and travels back to the left. So that's what happens again with the concept of reflection, whether it's a sound wave bouncing off a wall or a light wave reflecting off a mirror. Okay, that's what's happening. So it's reflected, and we're able to see an image, or we're able to hear an echo as a result of that reflection, depending on what kind of wave we're talking about. All right, so let's go back to our notes here and look at the next concept, which is refraction. Okay, this is different than reflection. So refraction happens when a wave, whether it be a sound wave or light wave, enters a new medium. Okay, so let me roll this up a little bit. Okay, so a medium, all that is a material. So let's say the wave is going from the air to the water. The air is one medium, the water is another medium. Okay, so a new substance or a new material. That's what a medium is. So when a wave enters a new medium at an angle, one side of the wave changes speed before the other side, which causes the wave to bend. Okay, so that's refraction. Again, a wave entering a new medium at an angle, and one side of the wave is changing speed. Okay, because think of going from the air to the water. Okay, the speed of the wave is going to be different in the air than it is in the water, and that's going to cause the wave to bend. Okay, because one side of the wave it enters the water and changes speed. Okay, and it bends. So let's just think of, in terms of refraction in the water, we take a look at the diagram here. We have somebody that's looking down at a lake or pond, and we have a fish in the pond. There's only one fish here. This is the actual fish. Notice the image. This is what we see. The image is actually shallower than the actual fish. Okay, so we'll fill this in real quick here. So submerged objects always appear to be shallower than they are, and this is because the light from them changes angles, right? The angle changes at the surface, which bends. Okay, it's bending it's bending downward toward the water. Okay, so again, we can see that as the person's looking down, the wave bends as it enters the water, and the reflected wave, okay, we can see the reflected wave from the image allows us to see the image, but the image appears to be shallower than the actual fish because of the bending of the wave. That's what refraction is, when the light wave is bent, because as the wave goes from the air to the water, the change in the speed causes it to bend. All right, and the actual image, the reflected image we see, appears to be shallower because of the difference in the speed and the angle. All right. Now, refraction at the water surface gives what we call the broken pencil effect. Okay, so, and that would result in something like we see here, where we have a pencil that's in the water. We notice the pencil above the surface, and then as we look down, we look below the water, it appears that the pencil is broken. All right, and again, that's a result of refraction, the difference in the bending of the light waves as they go from the air to the water and vice versa, and because they change speed, right, as they go from the air into the water and vice versa, which causes them to bend, which results in what we call the broken pencil effect. Because the pencil looks like it's broken, we know it's really not. It's just a result of refraction, the bending of light waves, which again, that's basically what refraction is. All right. So, another example of refraction, think about light being shined through a prism. Maybe it's a diamond or some other type of prism that has all kinds of different surfaces that the light, is reflecting off of. And what happens is, if I shine just regular white light, and white light, like just regular light, is a combination of all the colors of the rainbow, right? Red, orange, yellow, blue, green, indigo, violet, right? Roy G. Biv. So think about what happens here is when I shine light into a prism, okay? The light waves are refracted, right? Because the speed of the light wave changes as it goes from the air into the prism. And remember, light waves are being bent in different directions. And it basically separates the light. You can see red, orange, yellow, blue, green, indigo, violet. You can see all the colors of the rainbow. That's an example of refraction. Shining a light through a prism, light waves bend in different directions, and due to the difference in speed in the air and in the prism, and the light is separated into all its different colors. Okay, so again, white light, actual light that we see, is a combination of all the different colors of the rainbow. So let's go back, and one last concept we're going to look at in this section is called diffraction, right? So we had reflection, right? Waves bouncing off of surfaces. We had refraction, which was when waves bend, okay, due to a change in speed going from one medium to another. And then we have diffraction. Okay, this is when a wave moves around a barrier or through an opening in a barrier. It bends and spreads out. Okay, so if we think of, like water waves entering like a narrow opening, we just go down to the picture here. So we can see that as the waves move through this opening, they bend and they spread out. Okay, same thing. We can see a change in direction. Also, as the waves move through this opening here, again, they change direction, they bend, they spread out. And with sound, okay, so we can see this concept of diffraction with sound waves, is when sound actually bends around a corner. Okay, so sound actually can bend around a corner, and light waves actually have a much shorter wavelength. So that's why we can actually hear something even when we can't see it. Okay? So again, with sound bends around the edge of a corner, okay, and we're able to hear it. Light waves, okay, they have a much shorter wavelength, so we're not able to see what's around the corner, but we can hear what's around the corner. So let's look at a diagram here. So we have a radio playing, okay, and the sound waves, right? Sound waves have longer wavelengths than light, so the sound waves travel around the corner, so this person standing here can hear the radio. We can't see it, right? Because the light waves don't travel around the corner. We're not able to see the radio, but we can hear it playing. All right, so again, diffraction is just when waves move around a barrier, okay, or through an opening in a barrier, and they spread out. Okay, so again, sound can bend around a corner. Light waves, since they have a shorter wavelength, they cannot. Okay, which would explain why we can hear something even when we can't see it. Okay, and stay tuned for part 2 of section 17.3.